On April 12, 2025, Beijing made its sharpest break yet from the Western semiconductor world, cutting off all procurement contracts with ASML and halting TSMC-based chip orders across state-linked firms. It wasn't a bluff or a symbolic protest, it was a hard stop. According to analysts at Bernstein, this marked the most decisive shift in semiconductor sovereignty since the mid-1980s. But this wasn't an impulsive reaction. It followed a calculated year-long ramp-up of domestic manufacturing muscle. SMIC, China's rising foundry powerhouse, had doubled its DUV-based production capacity to over 300,000 wafers per month, a massive leap from its 2023 output, as tracked by IC Insights. For ASML, the impact was immediate and brutal. The company's EUV lithography systems, which account for nearly 70% of its gross margin, were abruptly cut from a key market. UBS analysts reported a 12% drop in advanced tool bookings from Asia during just the first quarter of 2025. Meanwhile, TSMC faced a strategic conundrum. Its $100 billion expansion into the US, once heralded in Washington as a pillar of national security, had become a geopolitical anchor. With Beijing blacklisting nodes above 7 nanometers, TSMC was effectively frozen out of a massive and rapidly maturing market. But what truly sent shockwaves wasn't the decoupling itself. It was that China seemed entirely ready for it. And what they've built in the shadows could render Western sanctions irrelevant. When the US first cracked down on Huawei in 2020, cutting off its access to TSMC's leading nodes and ASML's EUV systems, it triggered a forced innovation cycle so intense that Credit Suisse would later call it the costliest in modern tech history. Within just 5 years, Huawei and SMIC fought their way back. The Mate 70 Pro, launched in 2025, ran on a domestically produced 7nm chip built using only DUV lithography and self-aligned quadruple patterning. There were no foreign tools, no imported wafers. Tech Insights analyzed the chip in February and found a transistor density about 17% lower than Apple's A17 Pro, but functionally, it held up, especially in AI inference benchmarks. Soon after came the Ascend 920C, Huawei's answer to NVIDIA's H100. That chip went into full-scale production by March at Huawei's Qingpu facility, and Bloomberg confirmed over 30 domestic AI firms signed supply contracts in Q2 alone. This wasn't a patch or a workaround. It was a complete architectural inversion. China wasn't just catching up. It was starting to redirect the race itself. Even more surprising was SMIC's quiet move toward 3nm class fabrication without access to EUV at all. Expert consensus fractured. TrendForce insisted that the required multi-patterning complexity would make commercial yields at this level virtually impossible. But then came the leak. A prototype wafer, torn down in April, revealed gate just on the edge of 3nm territory, made possible through quadruple patterning. The process was slow, expensive, and inefficient by Western standards. Yields hovered at 40% and production time had tripled. But Beijing didn't care. Efficiency wasn't the target. Volume and resilience were. With state subsidies absorbing losses and domestic demand locked in by massive AI and defense procurement, SMIC didn't have to be profitable in a capitalist sense. It just had to be strategically viable. Morgan Stanley's March report put it bluntly. China doesn't need to match TSMC's cost structure. It only needs to scale a good enough alternative faster than the West can sanction it. That thesis gained ground after NVIDIA's dramatic exit from the Chinese AI chip market in late 2024, driven by US bans on its H100, H20, and B200 processors. The void was worth over $7 billion, and Huawei wasted no time. By May 2025, it was shipping the Ascend 910C en masse. Built by fusing two 910B dies into a single 2.5D package, it wasn't a sleek monolithic 5nm chip. But it worked. It hit 75% of the H100's performance at just 55% of the cost, according to China AI Tech Watch. Huawei's first batch sold out in 11 days, snapped up by state-backed cloud firms. More importantly, SMIC's adjusted SAQP yield rates climbed to 56% by mid-May, up from 31% at the start of the year. This wasn't technological parity, it was strategic asymmetry. China didn't need to outdo NVIDIA on every spec sheet. It just needed to reliably ship chips that were good enough, on time and under budget. The front line of the AI hardware war had moved, and Silicon Valley was no longer where it started. By the end of Q2, over 82% of the components used in China's sub-10nm production were sourced domestically, per the China Semiconductor Industry Association. SMIC's new megafab in Shenzhen, completed in just 16 months, was already producing over 45,000 wafers a month in the 5 to 7nm class. Shanghai Microelectronics Equipment, or SMEI, completed its first production run of 28 nm capable steppers in March, and was on track to hit 14 nm by late 2026. Meanwhile, China's talent engine had been quietly accelerating. Over 1,500 engineers from TSMC and UMC had crossed the strait since 2022, lured by contracts offering more than double their previous salaries. Under the oversight of SASAC, Beijing's $47 billion semiconductor fund was restructured in 2024 to prioritize vertical integration over global interdependence. The logic is now clear. This isn't just about chips. It's about reshaping the global order. China is no longer waiting for permission to compete. It has built a parallel semiconductor ecosystem under pressure, in defiance of sanctions, and by the look of things, ASML has long stood at the center of the chip-making universe. Its extreme ultraviolet lithography machines, powered by German Zeiss optics and Japanese photonics, are the cathedral tools of the digital age. No chips at 3 nm, 2 nm or beyond without them. But while the West built this dominance on tight alliances and precision tooling, China's strategy has been different. Slower, quieter, methodical, and now it might be working. In February 2025, everything shifted. A leaked internal document from China's State Key Laboratory of Laser Technology landed on analysts' desks like a thunderclap. A blueprint for a next-generation EUV light source. Not ASML's LPP, laser-produced plasma, but something entirely different. A laser-induced discharge plasma system. LDP. According to the leaked specs, it doesn't just tweak the architecture. It reimagines the physics. The claim? A 90% reduction in power consumption. A complete bypass of ASML's complex, inefficient tin droplet dual laser system, where only 0.1% of energy becomes usable EUV light. Instead, a two-stage process, low-power ionizing laser, followed by high-current discharge, producing plasma and EUV emission with up to 8% efficiency in lab conditions. That's not an improvement. That's a leap. Applied optics. Beijing reported EUV generation at 13.5 nm, matching global standards, with efficiency up to 8 times higher than current Western systems. Lab results, yes. But if scalable, it renders ASML's $170 million EUV machines obsolete. One leak, and suddenly global capital flows began to shift. But here's the real question. Is China just drawing blueprints, or building the future? ASML's EUV process, for all its brilliance, is also a power-hungry monster. One fully loaded EUV line pulls as much energy as a small town, 200 American homes worth per month. That's the cost of vaporizing tin at 50,000 laser pulses per second, bouncing photons off mirrors with sub-nanometer precision, and dealing with the constant degradation of optical components. Just 20,000 wafers, and a mirror needs replacing. But China's LDP approach? It bypasses the tin. No vaporization. No thermal nightmare. Just a stable plasma discharge, generating EUV at near-room temperature loads. Chen Wei, a former Zeiss engineer now consulting for Asia Lith, didn't mince words. If this works at scale, he told Bloomberg, it destroys the energy versus precision trade-off we've lived under for 15 years. ASML went silent, but in April, they quietly slashed their 2025 EUV shipment forecast by 18%, citing regional procurement uncertainties. Internally, they're already redesigning their light source architecture. Not because they want to, because they have to, and the timing couldn't be worse. TSMC's Arizona fab, the centerpiece of U.S. semiconductor reshoring, sits exposed. It's not just a $6 billion project. It's a political gamble. Joint production agreements, national security clauses, Washington calling the shots, neutral market logic, dead on arrival. ASML, too, is feeling the squeeze, sitting between Dutch export regulators, U.S. geopolitical pressure, and a shrinking customer base in Asia. Q1 2025 told the story in numbers. TSMC's foundry utilization dropped to 76%, down from 89% a year earlier. Why? Chinese contracts walked away. Canon, meanwhile, seized the vacuum. Their newly commercialized FPA 1200 NZZ-2C deep UV system, non-aligned, less restricted, quietly shipped 27 units to Southeast Asia. ASML's grip isn't broken, but the walls? They're crumbling. And what's worse than China leaving the table? Everyone else filling its seat. But let's not oversimplify. Building an EUV machine is hard. Running one at 30,000 wafers per month with 95% uptime? That's the Everest. China's LDP still faces brutal engineering realities. Like mirrors, multi-layered molybdenum silicon stacks with reflectivity tolerances under 0.2 nanometers. Or metrology. Tools for mask alignment still struggle to hit sub-angstrom calibration. Tokyo Electron said as much in April. China's tooling isn't there. Not yet. And then there's photoresist. Geopolitical and other domestic suppliers haven't cracked EUV-compatible polymers that can hold yield variance at industrial scale. Even if the light source works, synchronizing with etching, deposition, inspection, that integration challenge remains a dragon unslain. And yet, a $9.3 billion funding package across 4 pilot lines says one thing clearly. Beijing isn't testing waters. It's building bridges. As tech strategist Lisa Chow put it, China has proof of concept. What it doesn't have is repeatability under pressure. But the timeline? That can collapse. Just ask anyone who said Huawei couldn't make a 7nm chip until it did. So let's stop pretending this is abstract. If China cuts the cord from ASML and TSMC and builds something cheaper, cleaner, more efficient, what happens to the global tech stack? Because everything, AI, quantum computing,